Hey, yo, what's up? What's up? It's been a little while, but we're back in action. Um, so basically, today is the start of, I'm gonna be working on a project, for like an extended length of time. I've been wanting to do something like this for a little while since I started streaming. That was the kind of whole point of the, starting streaming is to, I don't know, just work on stuff on stream and kind of just show more of the behind the scenes aspects of what I do. Um, I want to get more into like doing music stuff, but um, the issue is that I haven't really worked on a whole lot of music stuff since like October. So I'm a little rusty. So every time I hop on, it's like I'm trying to like remember, I'm trying to get back like in the flow of things on stream, and it's just weird. So I need to like work on music outside of stream first, and that way I can like get back into the swing of things. But for now, um, basically what I want to do is work on this project because I initially started working on this game like I had the idea 2 years ago. I was playing. Let's see. Wait, why is it inverted? Okay. Um, this is just like a example demo from a JavaScript library called 3JS. If you've done any kind of development stuff, then like web development with like, if you've looked into any kind of like web development with 3D kind of stuff, then you've probably seen 3JS because it's so widely used because it's a really really great library, um, framework even. But so I was playing around in this and I was like, this is like really fun. Like I can't even count how many hours I've spent literally just hopping around this test map while listening to YouTube videos or podcasts and stuff. So I was like, if this is fun by myself, it's kind of like if you've ever been playing Minecraft while talking to a friend and you just hop around in a circle while you do it. That's kind of like the vibe I get from this. So I'm like, okay, well, if this is fun single player, then I want to see it multiplayer. And there's a few, there's a laundry list of reasons why uh, doing that is going to be difficult. But I'm always up for a challenge. Like I like really ambitious big projects that I can really sink my teeth into because if it's not something really big, then I lose like focus on it. I get less energized by it. But if it's something big, even though I might like make slightly less progress on it, um, like long term, I'm more likely to keep on working on it or something. If it's just a really small project or whatever, then I'm not that excited by it. Um, and plus, with this, I've already worked on this for like a month, 2 years ago. I was using like a completely different physics engine, um, and I had basically just mostly spent the entire month trying to figure out how to even get like server side and client physics and stuff like that. And like I spent most of that month like without even being able to like visualize what I was doing because most of it was just like back end physics server side code. But the good thing is that I have a lot of that like prior knowledge to pull from in terms of just like a general idea of how I plan on structuring things. And then in the past like week or so, I wanted to start this devlog like last weekend, but I ended up spending more time just doing research and stuff off stream. Um, but uh, 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 I kind of have a better idea of the frame, like the libraries and frameworks that I want to use now. Because originally I was going to use, I keep saying I was going to use a physics engine called Enable 3D, which is basically a wrapper for ammo.js, and that itself is a re-implementation of the Bullet physics engine, which is very popular over the years. Um, and Enable 3D was basically a way to integrate 3JS with ammo physics, and that was cool. But I found this other physics engine that's a lot more recent. And initially I wasn't going to use it. I was like, okay, I already know how to use Enable 3D. I'm already more familiar with it. It's more integrated into what I'm familiar with. But once I saw the performance difference in this new physics engine I'm going to use, like there's just no question, because the entire goal of this project was to make a multiplayer first-person shooter where you shoot these little mustard balls at each other. And so that's going to require just a lot of setting up. First, on this, like getting the physics set up. Second, on getting the server side stuff set up to where everything, you can play the game without it lagging. And like there's a lot of tutorials and stuff out there regarding like a 2D multiplayer game on JavaScript. But as far as a 3D game, there's not a whole lot of stuff out there. So it's already more difficult because of that. And then you add in the fact that I'm not just doing a regular first-person shooter game. I'm doing a first-person shooter game where we're constantly shooting projectiles with physics. So all of these have to be synced and replicated for each client, each person that's playing the game. And it just gets really, really difficult to make that happen without adding a whole lot of lag. But I've been doing a lot of research on like game networking stuff, and although I'm not really that great at programming at all, like writing my own stuff, I am really good at like puzzle solving, figuring things out. So, and plus I have ChatGPT. Like 2 years ago when I tried this, I was doing it all without ChatGPT, just kind of eyeballing everything, trying to figure it out. Because I don't ever really ask questions on forums or Discord or anything. Usually I'll just research until I figure it out. And I was making good progress, but back then I just kind of got tired of, like back then I had a different job 2 years ago, and I was just spending a lot more time working at my day job, and I didn't have a whole lot of time to just make stuff. And I got kind of burnt out because I hadn't been making a lot of like creative stuff. I was just programming. But now I'm in like a much more flexible job where I can work from home and stuff. So I have just like a lot more flexibility in terms of like time, and just like the type of work that I'm doing at my new job is just a lot more like creatively satisfying. And plus this makes for like a good like devlog kind of thing where like over time we can see the progress that I make. But the basic gist is to start out, I just want to have like a 1v1 type game mode where 2 players join in and they each shoot balls at each other, and they have like a limited, well not limited, you can shoot forever, but you get like 50 or 100 balls that you can shoot before the first ones start to disappear. So that's the pool that you're shooting from is constantly cycling. So that's kind of roughly the gist of it. Is just a 2-player first-person shooter game where you just shoot these each other, and the rest I guess we'll figure out on the way. But I definitely want to add controller support. I want to add like what's it called? Rollback, netcode stuff. What's it called? Reconciliation. Add. I shouldn't have started this so late, but I spent a whole lot of the day like figuring stuff out, configuring things. I went ahead and got the repo set up. Right now, all it has literally is just the README and a license. And this README is pulled straight from my, wait, let me turn this back on. Refresh. Okay. Pulled straight from my doc that I have going. But I think it lays everything out pretty well in terms of like what I want to achieve, and it has like the little example demo right here. For like the, oh, let me show you the comparison. Duplicate. This one's gonna be ammo. Okay, you see how laggy that was to start off with? See, lag, and then it kind of smooths out. And basically what I noticed is that this is with ammo.js, by the way. And so like there's a lot going on here. Obviously, like all of these things are pushing against each other and interacting or whatever. So it's a lot of calculations. And trying to run this on a phone it's not going to happen. But that's in ammo.js, in that physics engine. When I tried it in Rapier, this physics engine, I was able to get a consistent, oh wait, hold on, let me close out the other one. I was able to get like a consistent 30 to 60 FPS even in my phone. Doing this really, really complicated scene. Getting like around probably like 50 FPS. So when I saw that, I was like, even though it's a newer framework, it's has a lot less documentation, a lot less examples, a lot less resources and guides to pull from, it's 1,000,000,000% worth it. And not only because of the performance reasons, but also because Rapier is, let me see, dark mode. One of the main features that I thought was really awesome about Rapier is that it is deterministic. And what that means is if you have two different simulations going on, so you have your server and your client, as long as you do the exact same inputs to the system, as long as like the box that you spawn or the sphere that you spawn, as long as everything is like set up properly to where they happen on the same frames, then the both simulations from the server and the client will be like exactly one-to-one replicated. And for like the type of physics game, the first-person shooter that I'm trying to make, that is going to make things a lot easier. And to get started with that, I think, wait, hold on, let me do one thing really quick. One thing. Let me check when my music's not playing. Okay, you can hear that. Why can't I hear that? Oh, I know why. I think I do. Ah, okay. I figured it out. Now I can hear the music. Sweet. Sweet. Okay. No, that we have that up. Okay, so first, I guess what we're gonna do is kind of just get our background information on game networking. And what we're gonna watch for that is a really great resource from his name is Glenn Feidler. Basically, he was he worked for Respawn, the people that made Titanfall 2. I mean, they made a lot of other games, but like that was like the last game that he worked on that he mentioned in his website at Respawn. But like basically, this guy's been doing game networking physics for like nearly 2 decades. So he's got an incredible amount of experience. He's been doing like talks, like big talks, since like the mid 2010s. And I watched this 2 years ago, and I learned a lot from it. So let's jump into that really quick. I'm just gonna kind of play it on 2x speed. Wait, hold on. I wish I had hotkeys for this. Okay. Pause the music. Fast forward. And no audio. Hold
on. The 3 ways to do the synchronization.
There we go.
First one is deterministic lockstep. So if you remember real-time.
Okay. Actually, I'm not going to do it 2x speed. I'll do it like, hold on. We'll do 1.5.
You'll be thinking about lag hiding and a whole bunch of stuff, and that's at least 5 talks. So this talk is just about how to get a physics simulation running on one computer so you can see it on another computer. And that's all this talk is about. But it might seem easy, but there's actually a lot of very, very interesting detail. Many of you probably already know some of these techniques, the 3 ways to do the synchronization. The first one is deterministic lockstep. So if you remember real-time strategy games, thousands and thousands of units.
So this is this point is really, really important to what we're going to be doing, because the physics engine that I just mentioned, Rapier.js, it uses, like I said, it's a deterministic physics system. So as long as you keep both sides in sync, then everything will stay exactly the same. As long as you have the exact same inputs, as long as you have everything happening at the exact same time, everything will continue to line up without having to send a whole bunch of data back and forth. So he's going to explain that a lot more in depth right here.
They synchronize the game only by sending the commands, and it's very efficient in terms of bandwidth, but the game has to be completely deterministic given the same initial state. And
actually, I'm going to not play it at 1.5. I'll just do it at 1.
Synchronization. Okay. The first one is deterministic lockstep. So if you remember real-time strategy games, thousands and thousands of units, they synchronize the game only by sending the commands, and it's very efficient in terms of bandwidth, but the game has to be completely deterministic given the same initial state and the same inputs controlling it. It must give exactly the same result. So that's the first technique. The second technique is what I call snapshot interpolation, and that's a technique when you're sending from computer A to B. On B, you don't actually run any simulation at all, and all you do is you interpolate between snapshots, or effectively keyframes, of the visual state of the world, and then you render that interpolation. And that's a very robust technique, but it's also very high bandwidth. So I'm going to break into a worked example of bandwidth optimization in the middle of number 2 and show you how to get a network physics simulation down from 17.4 megabits per second to under 256 kilobits per second. And the third one, state synchronization. I used to do this one a lot. I thought it was the only way to do it actually 5 years ago. But it is a technique where you run the simulation on both sides, but you don't require determinism. You send both the input and as state as rapidly as possible to fix it up whenever it goes out of sync. So those are the 3 techniques. This is going to be a very practical talk. I've implemented everything I'll be telling you about today, and this is a little demo.
And this part is important because I found his demo that he made for this, and I'm able to run it on my computer, and I have the source code for it as well. He's released that, open sourced, and so like whenever I get lost, I can kind of refer back to the program that he has set up. Even though it's written in C++, a lot of like the architecture of it, it's very transferable. So especially with something like ChatGPT, I'll be able to kind of refer back to his example a lot, and it's just it's a very a good resource to have. I didn't know that I didn't have the source code 2 years ago. I didn't look for it, and if I would have looked at it more, I would have definitely had a much better understanding of what's going on.
Cube, and the collision with the ground induces the rotation, and you can see looking at it, it's tumbling, it's quite unpredictable, and that's a very important part of networked physics. It's not about a player capsule moving linearly through the world, or following a parabolic path. It's about complex tumbling motion that can't be easily predicted without running the simulation itself. Okay. So it's no fun unless you have some objects to interact with. And here's 900 small cubes. All of them are player interacting. They're not cosmetic. That's too easy. So I can roll around. You might notice every time I touch a cube, it turns red, and when it comes to rest, it goes gray again.
And we're not going to watch this whole thing right now. I just wanted to get basically his intro and get him to explain some of the core concepts, because he can explain them a lot better than I can. Because I'm learning all of this basically as we go. Like, I've read through this stuff, I've watched the video, I've watched his lecture, but I'm still a complete novice. So I'm learning this just as much as you are.
One of the network models, that's a really, really good part of the prioritization that's used. The interacting set of objects is very useful to have for many reasons, but it's also a very good visualization. Now, I wanted to push around cubes, move them, because in a rigid body simulation, you'll often throw something and it'll just keep going according to the laws of physics. So they're moving ballistically through the air. And I just use a little Hooke's law, a little spring, and I raycast to the ground, and I just push everything out from that using forces proportional to, I think, the square of the distance. So finally, one of the hardest cases is large joints of constraints where all objects are interacting with each other. And I really love the game Katamari Damacy. So one thing with this is not just attaching. They're actually physically simulated when they're in the ball, and everything is affecting everything else, so that it's actually quite a difficult case to network. So let's get on with the first technique. So this is the subtle art of synchronizing a physics simulation by sending only the inputs. You have to make sure that you're deterministic. And when I say deterministic, I mean exactly the same result given the same initial condition and the same inputs applied per frame. In here you can see it's not. And it's quite close, and then it gets further and further and further apart. A butterfly flaps its wings, and then it's completely out of sync in a very sad way. And it's a binary thing. You're not mostly deterministic. You're deterministic or you're not, down to the bit level, and I mean to the point where you could checksum your entire...
And this part is really important, because he's going to explain why getting a deterministic physics system set up is so difficult, and that's why I'm so glad that this Rapier physics engine does have that.
Physics state and compare checksums between the two computers, and they must be the same. So here is ODE acting deterministically. All I did was set the random seed for the solver, each frame, to the frame number, and that's all that's required to make ODE behave deterministically, with one caveat: on the same machine, with the same compiler, on the same OS, and so on. So I'll talk more about why determinism can be quite painful later on. So you can see it's exactly the same result. So in this simulation, the input that you're sending across is just a bunch of bools. Normally you might find it would be your controller, maybe your state of your axes and your buttons, or your keyboard state or whatever. But I only have to send this, and it's actually really small. When I send it across, it's important to realize that when you send packets over the internet, you can't just take the input on the other side and run that frame right away. There is a thing called jitter, and jitter is time variance of packet delivery. So if you send inputs 60 times a second, once per frame, which is exactly what we're doing, you're not going to get 1/60th of a second nicely spaced one a frame inputs on the other side. You're going to get clumps. You'll get 3 inputs, no inputs, no inputs, 1 input, no inputs, 2 inputs, and so on. And you need buffering. So this is a buffer. I use anything from 100 to 250 milliseconds. And when I dequeue, all the simulation on the right side is doing is saying, hey, do you have any frames now for this time? And sometimes the simulation on the right might have to do more than 1 frame, because you might have to catch up. So it's very important when you're doing this technique that your simulation is not CPU bound. You need to...
Okay, and then I'll use that to point to, basically just today I decided to use Snow Globe over snapshot interpolation, a library / framework from Gecko's IO. and I was originally going to use snapshot interpolation, this right here. But the other framework called Snow Globe, it's easier to basically run the physics simulation on the back end at a different speed from what the user is actually viewing. And here they call it display state interpolation. And that just means that the simulation can run at a different time step from the render frame rate. So for the user, it's gonna stay, so it stays 60 FPS, but on the back end for the physics simulation, that varies. It might go faster or whatever, it's just like catch up and speed up and all that kind of stuff. So that's one of the main reasons why I decided to use Snow Globe. Even though this one is primarily, like, all the demos and everything of it just feature 2D interpolation. It doesn't have anything for 3D. What I realized is basically I can use the functions to interpolate for the 3D rotation from the snapshot interpolation framework. Because this is just from the 3JS authors anyways. So basically, that was my only concern of using Snow Globe over snapshot interpolation, because this one had the code more natively for doing those 3D rotations. So I'm gonna have to do a little bit of configuring and implement this into this setup, but it's gonna be pretty straightforward, pretty easy, because like the math's already there. So yeah.
Be able to simulate n seconds of physics in less than n seconds of real time, otherwise you'll never catch up. At least twice as fast, I think, is good. Don't worry about rendering, you can just not render some of those frames. So here it is over TCP. Look at the right. Just watch the cube.
And TCP is the most commonly used framework, or what's it called? Protocol. It's the most commonly used internet protocol for most browser-based games, primarily because TCP has a lot of functionality built into it for like checking to make sure that all of the packets are received. And so that's really good for like a game, like if it's like a card game or something like that, or just some turn-based strategy game or something like that, where you just want to make sure that everything comes through accurately. But what it's not good for is fast-paced games. So that's kind of where it falls short. It adds a lot of lag, and you'll see that here.
It moves around. It's just 100 milliseconds and 1%, and this actually is pretty typical conditions. See the hitches. So you might think, oh, we'll just disable Nagel's algorithm and everything will be fine. Or there must be something I can do. There's not. This is just how TCP works. And it gets worse as the round trip time increases.
Yeah, see, look at that lag.
I'm not even simulating
That's
complicated
crazy
aspects of TCP here, like congestion avoidance and slow start and so on. I'm just simulating the fact that it's going to wait for an ACK, not get it, and go, oh shit, I have to send the packet again. And that's enough to get this behavior. And it's even worse here. In fact, it's totally unplayable. So for the love of God, don't network your game using TCP, unless it's solitaire. So that's just awful. Here it is at 250 milliseconds and 25% packet loss over UDP. It's completely perfect.
And that's what we'll be using.
What really frustrates me is people say, why do you just implement TCP? You're just doing TCP again. No, I'm going to do something completely different. I'm going to do reliability differently. Send every input that hasn't been ACKed. Every single packet has every input that has not.
And when he says act, that means acknowledged. So basically with TCP, it has the built-in functionality to ensure that the other side has received the information that you sent over. And basically what he was saying right there is a lot of people would tell him, why are you going to just use UDP if you're just going to re-implement the baseline core features of TCP? And what he's saying is basically, wait, what did he say exactly? He said, basically, you just resend all of the inputs, because inputs don't take a lot of data to send over. Like, you're not sending all of the rotation and position information because that number one takes up a lot of data. Number two, if you just send the position, rotation, and velocity of the objects in the scene, if the physics simulation, even if it's deterministic like Rapier, like the one we're using, if you just only send over the positional, rotational, and velocity information over to the client side, it won't stay locked deterministically. It won't stay in the exact same state. And so what he's saying is you just constantly send, like if somebody presses W to walk forward or clicks to shoot something, you just constantly send that information until it's been received, and then you can quit sending it. So basically, like if I was to press the W key to walk forward, then it's going to continue sending that information saying, hey, I walked forward at this frame, until the client gets a message back saying, okay, that one has been acknowledged, we can move on.
Something completely different. I'm going to do reliability differently. Send every input that hasn't been ACKed. Every single packet has every input that has not been ACKed. So if one packet is lost, the very next packet has the input that you're going to have to wait for before you simulate that frame. And the inputs are very small, so you can get away with it. And if you're worried about the size, you can encode them, because inputs change rarely. So it's usually going to be 1 bit for every input, not changed, not changed, not changed. So it looks like this. From the receiver's side, with around 100 milliseconds of latency, the ACKs don't get through to the sender, so he just keeps sending more. And we get about 6 frames worth at 100 milliseconds, and we get a steady state. And now my input delay buffer says it's time for me to simulate frame N. From the sender side, once we reach a steady state, it looks a lot like I'm going to simulate frame 5. I got an ACK for 0. I don't need to send 0 anymore. It's really simple. So that is literally all there is to this technique. It's the simplest networking technique. It's extremely low bandwidth. The best part is that bandwidth is not dependent at all on the number of objects in your world. So you can have millions of objects, and as long as your simulation is deterministic, the input is just the size of the inputs, and that's usually very small. The cons: floating point determinism is incredibly hard. I have it working here because I'm showing on the same compiler 2 processes in the same process, ODE running in a very nice way. But that doesn't mean that if you compile with Visual C and GCC that you'll have a deterministic result, because the compiler will apply different optimizations to the floating point and get a very slightly different result. It is possible, but it's very hard. Also consider that graphics cards are not just being used for graphics anymore. They're being used for physics. And I'm fairly certain that an NVIDIA card running CUDA running physics is not going to give you exactly the same result down to the bit level as an NVIDIA card or an AMD. Even on different OS, you get a different result. So it's a good technique if you're on a very fixed platform. So a console game running on one console could probably use the GPU and get a deterministic result. But otherwise, I wouldn't recommend it. It's also not very good for high player counts, because you have to wait for the most lagged player. And as you increase the number of players, statistically...
And this is partly why I'm mostly just focused on a 2 to 4 player game at first. That's all I really care about, is 1v1s and 2v2s. Because it's just going to make things a lot more simple and straightforward. And that's kind of what I had imagined in my head initially anyways. So it's a Like I never really intended to make like a big like 5v5 or 6v6 person game mode or anything like
Deterministic
that.
lockstep MMO. As you increase the number of players, result. Otherwise, I wouldn't recommend it. It's also not very good for high player counts because you have to wait for the most lagged player. And as you increase the number of players, statistically speaking, the probability that you're going to wait for input from any one of them approaches 1. So there's no such thing as a deterministic lockstep MMO. So the next technique, snapshot interpolation.
This is what I was planning on using until I switched over to the new physics engine that I'm using, Rapier.
In this technique, we send the visual state of the simulation, and we don't run the simulation on the right side. So the position, the orientation, quaternion, and I have to send the interacting flag because the simulation is running and it doesn't know what should be read. So I have to send that too. Anything that you can see, you need to send. Notice that I'm not sending linear velocity and angular velocity right now because you can't see that. In the packet, I'm going to include the state for every object in the world. And you can do a little bit of math and realize this is a very, very large packet. We're going to optimize this very soon. Here's what it looks like if I send snapshots over the internet 60 times per second. And you'll see that it's really jittery on the right. That's the same jitter that I talked to you about for input. You don't receive 60 packets a second at a nice rate, so you have to have some buffering. But think for a minute. Let's say we drop down to, let's say we do some buffering, just like we did for input. What if we lose a packet? So if we lose packet 100, we don't have anything to render on that frame. So we have to do something to go between samples, which is interpolation. So let's drop down to 10 packets per second. And it looks almost promising, right, on the right side. It's hard to believe that you could get a smoother result from this, but it's possible. So when you interpolate, you need to have at least 2 samples because you need things to interpolate between. That means if you're sending packets, snapshots 10 times per second, you're adding at least a minimum of 100 milliseconds on top of network latency. This is not negotiable. You're interpolating from from snapshot 1 to snapshot 2. You have to delay until snapshot 2 has arrived. Unfortunately, although this works great when there's no packet loss, you always have something to interpolate between in the window. If you have a lost packet, you have a hitch because there's nothing to interpolate towards. One solution is to increase the amount of delay. So if you have 2 snapshots worth of delay, you're protected against 1 lost packet. You see that I can actually skip over it and interpolate to the next one. If I have 2 lost packets in a row, I need 3 snapshots worth or 300 milliseconds. And this is getting a little bit high. It's not an acceptable amount of latency to add to a simulation. But it does work. So let's just start with this, and then we'll optimize bandwidth, and we'll optimize this time down over the next 5 minutes. So here's what it looks like with linear interpolation. It looks okay. Look closely at the cube. You can sense it's not quite right. Like it's a little it's like doesn't look perfectly right on the right side. So a little bit of sort of first order discontinuity. Notice that when you roll in the Katamari, you see this kind of pulsing. And that's actually the cubes on the outside taking the shortest linear path through the cube instead of rotating around it with the interpolation. So there's some artifacts. We can actually do a lot better. So this is what it looks like at 10 snapshots per second with linear interpolation. I would like it to look like this. So there's a way. We need to send linear velocity now as well. And at each snapshot, we're going to use Hermite, I don't know how to say it, interpolation. It's French, so I think it's Hermite. But if you do that, it looks like this. And it's basically perfect. And all it is a spline that interpolates through the positions while respecting the linear velocity at each sample point. And you get basically a perfect result at 10 packets per second. There's no simulation running on the right side at all, it's just interpolation. So I can't see any artifacts.
Yeah, that's pretty good.
But there's still way too much delay. So I don't think anybody...
Okay, and he basically continues to optimize this system for the snapshot interpolation. I'm just going to skip to the last part he talks about because that's what we're going to be using. Let's see. Okay, and here's, I think, what we're going to be mostly focusing on, because state synchronization, like, it can be used and built upon by like a deterministic system. So I'll let him explain that more.
Good. So we have one last technique, state synchronization. So this is a technique where you run the simulation on both sides again, but you don't wait for the input, like with deterministic lockstep. You don't require determinism. You just keep running ahead. So if the input doesn't arrive for that frame, just go ahead. Just keep using the previous input. And to compensate for that, because obviously you're going to go out of sync right away as soon as an input is lost, we send state across as rapidly as we can to sort of fix it up. So if it goes slightly...
And this is another big reason why I chose to use Rapier.js, is because it has a built-in function for that snapshotting, and which they say right here. So that's kind of like the main reason that they have this feature, is so that you can send those snapshots and keep everything the same. The issue is that sending these snapshots, it takes up a lot of data. So what he's and also it's hard to keep everything 100% deterministic. So but I'll let him explain some more.
We're correcting everything, and we try to prioritize the updates so that we update the most important objects more frequently and the less important objects least frequently, which means that this technique actually uses less bandwidth than snapshot interpolation. So here's sort of the end result. And this is using no complicated technique of bandwidth optimization except for the smallest three and quantizing the position and the linear and angular velocity. And the cool thing is I can just say, okay, no more than 256 kilobits per second. No more. Don't ever send anything more than that, and it will just dynamically lower the frequency of updates per object to meet that. So if you have a bandwidth target that you have to meet, this is a very good technique because you can set a dynamic ceiling. You can actually change that on the fly too. So how is it implemented? Because we're running the simulation on the other side, we're not just sending visual state, we're sending the full state of your rigid body simulation. So we're sending linear and angular velocity as well. I don't need to send the interacting flag anymore because the simulation is running on the right side so it can work it out. It knows when things should be read. So the packet, with this approach, we don't send every object in every packet. We just pick the n most important updates. And how you define the most important update is up to you. In my simulation, that's why they're colored red. So obviously the red objects are much more important than the at-rest ones. Maybe in your simulation, distance could be a factor, or the type of object. Player objects are much more important than non-player objects. Maybe vehicles are very important. It depends on the simulation that you're networking. But it's just a priority function. And notice that we're sending the number of state updates per packet. We're not always going to send 64. We're actually going to fit as many in as we can each packet up to a maximum packet size. That's how we do the bandwidth limit. So you might wonder, how do we get the n most important updates? What we want is really important objects getting frequent updates, but we want to be fair. We want all the other objects in the world to get updates every now and then. And we want to be able to tune that with a different priority per object. So my solution that I use is a priority accumulator. And that's just it's an array of doubles, one entry per object. It's nothing complicated. And the key thing is that these values start at 0 and they persist across each frame. So they remember the value. Each frame, just add your priority and sort it. Take the top n, put them in a packet, drop the ones that were sent back to 0 priority. Notice that some of them didn't fit, and then a few smaller ones later snuck in at the end. That just saves a little bit of extra bandwidth. It's a good trick. Just go from left to right, most important in your top. So you might say, I probably can only send 32, but I'll just try 64, and then you'll stop at some point and go, all right, it's done. And sort it again, and the ones that were sent get to bubble up. The ones that weren't sent, probably very likely to be sent in the very next packet. It's a really simple technique, but it's very effective. So with this, we have a jitter buffer, just again because jitter exists, and we want, if we're sending input and state for frame n, I want it to play on frame n, not plus or minus 1 frame. We don't want that source of non-determinism between the two simulations. So there's a very small amount of buffering in a jitter buffer, maybe 2 or 3 frames at 60 frames per second. That'll give you enough delay, and it's much smaller than you would have with interpolation. And so basically, 3 frames ago, the simulation on the right side is just going to go, I want to do frame 100. What is the input for frame 100? How many? I've got 20 state updates for frame 100, and it just snaps them. It doesn't blend the positions or smooth or any. It actually snaps state hard. That's key to this technique. You want to make sure that on the right side, because you're running the simulation and you're extrapolating from the state that's forced from the authoritative simulation, you want to snap the position, orientation, linear and angular velocity hard. You don't want to kind of go, oh, just move halfway towards it. Like, just snap. That's really, really important. So if you look on the right side, as the Katamari increases, you'll notice that there's a lot of wobbling. It's smooth on the left side, but it's very, very jittery on the right. And that's because the extrapolation is starting from a quantized position, orientation, linear and angular velocity. It's getting a very slightly different result, and then the next time a state update comes in for that cube, it's corrected a little bit, and you see the pops. The solution is to quantize your simulation on both sides. Take the quantization that you're applying with your network packets and apply exactly the same transform over the entire simulation on the left side, because you want to make sure that it's running from what the other guy will receive. And then on the right side, between frames, so that you match what the left side's doing, quantize everything. This is expensive. If you're writing your own physics engine, maybe you could just do your physics in integers instead. But here, you just have to kind of take all the state, quantize it as if it was going over the network, and then force it back into the simulation. Otherwise, you have that jittering with this technique. Also, because you're quantizing, you're feeding that quantized result back into the simulation. You need a lot more precision than you did with interpolation. I think I used 512 units per meter. I multiplied that by 8. Otherwise, I saw jittering on the left side, not even the right. And the orientation, I actually had to write a 64-bit version of small as 3 because 10 was not enough. So now you can see that the jittering is not there, but I've got 5% packet loss going on here. And sooner or later, I'm going to lose an input. And what's going to happen is that jittering is going to start happening from that point forwards. So I've delayed, there's no packets getting through, and snap. Now notice that the jittering is back. So what's happening here is I'm only updating a subset of the objects in that ball in each packet. I don't have enough room in my little packets to update 100, 50, whatever, how many objects are in there. I'm updating 5 over here, 10, 5, 20. So you've actually got sort of like a cascading failure. You've got enough out-of-date objects that were pushed out of the correct place by the previous incorrect ones before they were corrected, and then that just cascades. And that's because we're not sending all of the state updates for this island at once. We're kind of distributing it with that priority function. So, and if you think about it, if your simulation is just a little bit non-deterministic, which it usually is, you'll get the same thing here. You'll get just a very slightly different result. So there are 2 things to do.
Okay, and I just realized something. Basically, the way that my game is going to be ran, what he was talking about a second ago with the priority accumulation, where it sorts it by the objects by the most important ones that need to update. That's going to be really easy for my simulation because the most important objects are going to be the ones that the player just fired. So that's already pretty simplified for me. Like a ball that somebody shot like 30 or 40 balls ago, it's just bouncing around somewhere on the side of the map. That's not going to be nearly as relevant as one of the first like 10 or 15 most recent balls the player shot. So I already kind of have some idea of how to achieve something like this, like or like it's kind of more built into my gameplay. I don't necessarily, it's not going to be like just a ball pit, basically like he's demonstrating here. So that does simplify things.
Pop. Like, it's extremely bad because all your islands of objects will very aggressively try to resolve all penetration caused by very slightly different results, and that will induce more penetration and popping that cascades. So I actually changed ODE so that it pushed out the anti-penetration constraint was a lot softer, and that was required to make the right side look smooth. The other thing I did is smoothing. So why I said earlier that you should pop is because when you pop, like here, you can keep track in local space of the error. And you can reduce that over time. So what you do is you kind of remember the error.
Okay, I think we've watched enough of this video for now. So let me turn the music back on, make it a little bit lower. Okay, so for what he was just talking about there was state synchronization. Like I said, I was initially going to use this library, this framework, snapshot interpolation from Geckos.io. But I found this one like last week, and this is just a re-implementation in TypeScript from this other project called Crystal Orb. And this handles the client-side prediction, the server reconciliation, and the display state interpolation. So client-side prediction, our clients, the people that are playing the game, they'll both be running this physics simulation. So basically, whenever I click to shoot a ball, you see it instantly update on your screen, and then after a few frames, when it gets the information back from the server, then the position of that ball is updated to match what's officially on the record. So that's kind of what a lot of games do that have projectile physics, is that they will kind of do the guess, shoot it off first, so you get a instant kind of visual feedback to say, hey, your shot's been fired, and then the rest of that, it'll get synced back up and corrected as time goes on. Where are we at? Okay, and then server reconciliation, that's what we were talking about. So server runs slightly delayed, and just like you said, it doesn't have to be a whole lot. It can be like 3 frames or something like that. A lot less than trying to do a raw snapshot interpolation. And the server sends the official copy of the state of the game to the client. And then, like you said, it just snaps. Like he was just showing in that video. You don't have it like float towards where it needs to go or anything. It just immediately snaps. And that's just the way you got to do it to keep everything in sync and keep the game running at the same kind of state. And then display state interpolation, that's going to be really, really huge for us. And this is kind of a really big factor in a lot of physics games in general. Like I watched the video of some of the physics networking engineers that worked on Rocket League. And one of the things that they figured out when they were making their game is that if you have your physics simulation running at the same speed as it's being rendered, so if we're playing this and our physics is being calculated at 60 frames per second, and we're playing back at 60 frames per second, you have some issues where the like if I click right here, the ball might hit the wall at like half of a frame, so then the ball will be kind of poking halfway through the frame. Hold on, let me see. Let's see if I can find like a diagram of this. Let's see, game physics. Better. Okay, I'll just use this. So like on frame like 59, you might be right here, and then frame 60, the ball might be like halfway through. And basically, that happens because hold on. This would be a lot easier if I just played the video of like the Rocket League networking engineer. They can explain it a lot better than I can, because I only have like I said, I'm a complete noob at this stuff. I'm just learning it as I go along. Is this one better? But we'll figure it out as we go along, and we'll get a better understanding of it. But the main thing that you need to know is that in order to keep things from clipping through, you have to have your physics simulation running faster than it's being displayed. It has to be running faster than 60 FPS. And that's one thing that this framework has as a feature, is that the simulation can run at a different time step, at a different speed than is being rendered. And that's also really important for our state synchronization, because what's going to be happening is, let me see if I can get his diagrams over here. So the main, the official game state on the server is always going to be running like a 2 or 3 frames behind what the players see. So it's going to have to be able to kind of play catch up and render multiple frames really quickly sometimes in order to keep everything at the right speed. You don't want to get too far behind. So that's really important that this framework allows for that kind of like catching up and altering speeds. And that's something that this framework, this library, does not have. It has client-side prediction, server reconciliation, lag compensation. You can press and encode your stuff, but it doesn't necessarily have the same kind of ease of access to make the server's physics ran faster. Okay, so we're on the same page with that. Let's see. Okay, and then so for the server architecture itself, we're going to be using geckos.io, and it's built by the same guy that did that snapshot interpolation. But this is his server, and it's using UDP, and it's set up very similarly to what's it called, socket.io. So I've found like a couple of tutorials and like guides on making a JavaScript multiplayer game using socket.io, but the main difference between socket.io and geckos.io is that socket uses WebSockets. That's TCP. And just like he explained in this video, it's not very good for like first-person shooter games or anything that has a lot of really fast updates. So I'm using this one because it uses UDP instead, so it's a lot faster. A lot like that has a lot of downsides, but they can be overcame, as he explained it in this talk and in his blog articles. And we're going to be reading over the articles as we go along. I just liked his talk right here with the visuals, examples right here. It explains things pretty well. But I might eventually later on, after I get the core version of the game configured and set up, I might swap the netcode for the networking to netcode.io, which is a framework developed by this guy right here, Glenn, his name, Feidler. I always want to say his name is Fielder, but Feidler, Glenn Feidler. So he made this network protocol called network.io. Actually, this is it. This is somebody's implementation of it in TypeScript. So that's what I would be using when I switch to it. But for now, I'm going to be using geckos.io because it's a lot more straightforward. It's very similar in its API and usage to socket.io. So I already kind of have a decent familiarity of it. And there's a lot of like similar implementations that I can look at and use as an example. But with netcode.io, it's kind of over my head for right now. It's probably mostly set up this like in a similar way, but and it definitely has like some added features over Geckos. Like it has a lot of like extra safety and security protocols. But since this is basically my first game and it's really, really complicated already, I'm not going to be worried about anything like that. I just want to get the game made first with whatever makes the most sense to me. It doesn't have to be the most perfect implementation, but just what makes sense. And Geckos seems to make more sense. So that's that. And for the physics, like I explained earlier, we're using Rapier.js, which is really, 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 really fast performing. Mostly because the underlying physics engine, it's written in WebAssembly, and assembly code in general is like it's hard to write, hard to work with, but it's extremely fast because the computer, the processor, it can handle the code a lot more effectively because it's less rewritten for a human to understand. It's more like just computer language, if you will. But so the underlying physics engine that we're looking at is written in WebAssembly and kind of implemented in Rust, the programming language. So that's all fine and dandy, but I don't know Rust. So what we're going to be using is a version of this physics engine that has been basically wrapped around the Rust version with JavaScript. So that way I can use basically the same terminology, the same syntax that I'm familiar with in JavaScript, but you get this really, really fast, highly performant physics engine. And even though it's being wrapped in JavaScript and then it's written in Rust, but then being like compiled in WebAssembly, the underlying physics engine is so fast that it's still able to be really, really performant even on mobile devices. So that is that's that. This is just kind of some extra stuff that I wanted to add eventually, just because I like the idea of like whenever I was younger, it was nice whenever you could like take your Xbox over to somebody's house and then like play split screen and stuff. And split screen is kind of gone to the wayside, and it's not in a lot of the games these days. So I want to definitely have a split screen multiplayer feature, and also I would like to have like offline LAN lobby abilities. So like the old like Halo Combat Evolved and stuff like that. Like basically the reason why I do this is like in case like you and a friend go on like a camping trip and you want to play like some multiplayer game, ideally you could just like both get on your phones with a like an Xbox controller and then just play the game together, even though you don't have any internet. That's kind of the one of the main reasons I want to add this, because I've been in situations before where like I was out in like a cabin or something, and it's like at the end of the day you want to play some games, but there's not like a whole lot of options for just like offline LAN stuff these days, especially in like a mobile gaming format, at least from what I've seen. But I feel like there's been a lot of optimizations within the past like 2, 3, 4 years or so in like web-based game development stuff. Like this physics engine, Rapier, it's only like 2 years old. So like a lot of this stuff, a lot of people's idea of like browser-based games is that like they're just incredibly slow and there's not really a point to like try to make a really complicated game on it. But there's been a lot of like optimizations and improvements, and I think it's a lot more viable these days than people seem. So what the task that I'm taking on is really, really difficult, especially because it's like a lot of like physics-based projectiles that we're going to be shooting. So I mean, it's just a really, really difficult challenge, but it's going to be a really, really wonderful proof of concept, a great learning experience, and just a fun game overall. So it's just going to be a difficult project, but it's going to be a rewarding one. Like if I'm able to get anything that works even remotely, I'm going to be proud of it. So that's kind of why I'm excited for it. Yeah, we're going to be using React 3 Rapier. React is a framework that lets you basically, it lets you easily add a lot of really nice UI functionality to whatever you're working on. I recently started learning it like within the past month or so, and getting used to it, and I like it. It makes doing like UI stuff a lot easier. I was initially against it because Facebook made it, and I was like, oh, I'm just gonna like boycott that. But I was like, eventually I realized there's not really a point to not use something just because some company made it, because there's so many different frameworks and libraries and stuff where like a lot of these companies are like collaborating on anyways. So I mean, it's kind of pointless to write it off just because it was developed by Facebook. It's not like all of the data is going is being collected or whatever just because Facebook wrote it, you know. It's like they have that stigma, but still it's still like the core functionality is really good. So I'm going to be using that, and React through Rapier is specifically a like basically it adds a wrapper for the Rapier physics engine to be used in a similar fashion to React components. So needless to say, it's well, basically it's achieves a lot of the what you call it, I'm drawing a blank. It takes a lot of the extra stuff that I was gonna have to set up myself of aligning like the visual rendering of 3JS with the physics engine. It kind of handles a little bit more of that just off rip. We're going to be using TypeScript because it's I like it. It can get complicated and technical sometimes whenever there's like some weird library that you're using that doesn't have types. But and I've had like so many headaches with it, but by and large, I really like using it. I appreciate a lot of the features and functionality of being able to like see like the definitions of whatever like object or component that I'm using. It's really nice. This I'm going to be using Vite, mostly just because there's going to be a tutorial I'm going to be following starting out, and he already has a nice little template framework set up. And as part of the offline split screen multiplayer and stuff, I want to have this game as a progressive web app, so that way it's all browser based, it's all written in JavaScript. You can access the website, but just like this GitHub page right here, you can install it to your device, and it has a really, really like to the end user, it looks really similar to an app. Like it makes a shortcut, you can store local data. There's just a lot of similarities. It's not like full access to the device like a regular native app would be, but I just really, really like the accessibility of it, that you can just write it, put it on the web, and then any device that has a supporting browser, and just install it as an app and then have things saved offline. So it gives me a really straightforward way to incorporate that offline ability, but still be like in a website, easily accessible form factor. I can even put it on like the Google Play Store, like the App Store. So there's just a lot of reasons I want to use that, because I was looking into it earlier, and I can also, instead of using a progressive web app, I could use like React Native, which is basically another framework that Facebook made based on React, where you can write an app one time in one language using React syntax, and then it's able to be compiled and installed on an iOS device or an Android device or whatever. But there's some extra drawbacks, because it's not like you can have it load on a website, but it's, I don't know, it's I just like the idea of having just a website that you go to, and then you can just install that if you want to. You don't have to go to any like third-party thing. You don't have to go to the App Store. You can just, if you find the game, if you come across it, you're playing it, you like it, you can just install it right there from the same page and save it offline, and then play it whenever, wherever, and hopefully potentially even offline, peer-to-peer, local multiplayer. So with that all out of the way, explaining the project, explaining some of the reasons why I'm using some of the frameworks and libraries that I'm using, we can get into actually setting up the rest of this repo, setting up the project, because currently we just have the license and the README. And wait 1 second, let me turn back on dark mode. There we go, sweet. Okay, so we're going to be following this.
But have no idea how it works? Hi, today we will have a look at an important aspect to build the many kinds of video games: physics. It can sound scary, especially if, like me, it was not your favorite subject at school. But thanks to libraries like Canon and Rapier, it's very convenient and easy to add physics to your Three.js projects. Let's start by getting my React Refiber vid starter from GitHub. Run yarn and yarn dev, and you should get a cube. We will use the physics engine Rapier, and thanks to Poimandres, again, they made a React wrapper. To install it, run yarn add at React 3 Rapier. Now we only need to wrap our experience into the physics component. The default gravity setting is the Earth one. Wrap it into suspense to be sure every models and assets are loaded before the engine starts calculation. In experience, we add an ambient and directional light to make our scene less flat. We replace the cube with a rigid body from Rapier containing a box. A rigid body is an object in a physics engine that behaves like any object in the real world, with properties like mass and friction that determine how it moves and interacts with other objects. When we run it, we can see it falling because gravity affects the rigid body. Let's zoom out the camera, and because we want that box to be our floor, change the rigid body type to fixed. You can see the documentation for the 4 different types. What fixed means is that it won't move, but will still react to collision and impact other dynamic objects. Let's add another cube on top of the floor. By the way, the color name I use are CSS color names. Our new cube falls into the floor and stops. Because we have the prop debug on the physics engine, you can see a red border around our cubes. These are rigid bodies. Now let's add a sphere. You can see that the rigid body collider applied is still a cube. We can change it to ball, and now the sphere had the correct collider. Let's see how our object interacts together. If we put the ball on top of the cube, it will stop on it. And when we slightly move it to a side, it will fall and react like in the real world. Let's separate them again and add a torus with a hull collider. What it does is it will wrap the external mesh shape, like a gift wrap, but you can see the center hole is ignored. If you need a very precise rigid body, you can use the tree mesh option. It will wrap perfectly to the shape of our object. But keep in mind that the more complex it is, the more CPU intensive it will be. The good approach is to use the simplest shape that works correctly. For example, if you have a 3D character, you can in many cases use a simple capsule collider. On rigid bodies, we have many props to define how the object reacts.
Yeah, so for the game that we're making, or at least the players and the projectiles, it's going to be very straightforward. For the players, it's going to be like just a basic capsule like he's talking about, like a pill shape. And then for all of the projectiles, all the balls, they're literally just a sphere. So not very complex in the geometry department. I thought about adding something else to make the actual, like, be able to use a really complicated game level, like a really complex map. It has really simple geometry, but I decided against that for now. I'm just gonna have simpler maps and everything, because trying to implement that other library, it might add some extra like complication and conflicts between the collision physics, or the collision detection calculated by Rapier itself. So I'm gonna hold off on that for now. I was gonna use 3 mesh BVH. Okay. Let me show you. Display. See, so what this is this is a pretty complicated like geometry. Not super complicated, but it's not, you know, just a basic square, a basic box or whatever. It's got like leaves and all that kind of stuff. But what it does is it takes a more complicated geometry like this and then breaks it down into smaller cubes and uses that for the physics calculation stuff. And like I said, I thought about implementing this to be able to have like a more complicated geometry like this just off rip, and it just gives me a lot more flexibility in doing like level design. But I think it's going to add a little bit of conflict in it's going to be something that I want to add later. I can always add it later, and it might add complications. So for right now, we're just going to keep things simple, and if we want to add this later on to get more complicated maps that have a weird geometry like this, then we can do that as needed. But it's not something that I necessarily feel like is a core component, because graphics and graphic fidelity isn't a main factor in this game project that I'm working on.
Collider. On rigid bodies, we have many props to define how the object react in the world and with other objects. For example, restitution, if we set it to 2, items will bounce on it. Let's decrease the gravity on the physics engine. Items now fall slowly. We can make it very slow and even make the gravity affect the x-axis to make items slide into the right. Set it back to normal. You can also define it specifically for a rigid body with gravity scale. Set it to 4 on the ball and you can see it bounces many more times than the other objects. You can also combine colliders into one rigid body. Let's add our cube and sphere together. Set the colliders to false because we want to manually create them. We set the sphere Y position to 1 and add a ball collider. So far our two objects are grouped into the rigid body and move together, but the physics apply only to the ball collider. We can add a cuboid collider and now the colliders represent correctly our object shape. If you find the video useful so far, please hit the like button as it really helps the channel grow and be visible to more fellow developers. Let's build a simple game. We remove all objects except the floor and add a cube on the left. We will want to make it jump when we click on it. Start by creating a hover state and update it on pointer enter and on pointer leave. Then change the color of our cube. On click, we will call a jump method. We will need a reference to our cube, and to move an object in a physics engine, we don't manually change its position. We apply forces instead. Use cube.current.applyImpulse with x, y and z directions. We use 5 for the y to make it jump. Let's remove the restitution of 2 on the floor. Now our cube color changes on hover and jumps on click. We can jump while it's already in the air, we will change it later. Let me show you another interesting way to interact with physics. Let's change our impulse to go to 4 on the x-axis and 0.1 on the y-axis. By default, it will just make our cube slide. But we can change the floor friction to 2. And now the floor is not slippy anymore and makes our cube stop and rotate. Let's restore our jump impulse and start our game. We will create a kicker that will rotate and eject our cube from the floor. We will use the type kinematic position. What it means is that its movement won't be physics-based, but the object will still impact other physics-based objects. Here is what it looks like. Let's make it rotate. In useFrame, we will get the current rotation from it. We use the quat method to convert the rapier value to a Three.js quaternion. Then we create an increment rotation that will be the rotation we want to apply, and we multiply our current rotation by it. On the kicker, as it is a kinematic object and not a dynamic one, we won't apply impulse, but use setNextKinematic rotation instead with the new rotation. Now it slowly rotates and I jumped too late. It kicked our cube. Let's change the rotation speed to 5. We will start the game only when we click on the cube. Define a start state and set it to true on click. In useFrame, return if start is false. Now the rotation plays only when we click on the cube. We want to jump and move our cube with keyboard keys. Go to the app components. As I'm not using TypeScript, I can't use the enum from the doc, but we can create an object containing all the different keys. We defined a memoized map array of keys, that way we can change the keys at only one place without affecting the rest of our game code. Wrap our canvas into a keyboard controls and edit the map prop. In the experience, we now have access to the use keyboard controls hook. We declare a jump pressed and check if our state of control.jump is true. In the use frame, if it's true, we will call the jump function. It works, but because it's jumping even in the air, it jumped too many times. We can use different approach to check if we are in the air. I decided to make it simple to use the collision.
Okay, while we were watching that, I went ahead and downloaded his code and added it into this project. So let's go down here, yarn install. That's going to get all of the packages that he had from his project and get everything. And that's going to include the React 3 fiber, the React 3 rapier. Going to include the Vite stuff. Okay, sweet. And now yarn dev. I guess I could just control click. There we go. We have a 3D scene. Awesome. Let's see. I think I could split it and have like a browser over here, but I don't feel like it right now. We'll just keep it using this browser. Make a new terminal. I don't need bash. Sweet. So with with that, let's go ahead and commit that to our project. So, what was this project called? Okay, we will say we added assets from React 3 Fiber Vite Starter. Yes, all that looks good. Oh wait. Okay, we staged all the changes. Yep. Changes. Boom. Double check. I mean, I don't have to double check. I know it worked, but boom. I just learned how to use Git like semi-recently. Actually, I learned originally how to use Git so that I could save the old version of this project 2 years ago. Like right before I quit working on this project, I learned how to use Git because I had been just doing that thing where you like copy the folder, like make a zip file of it, and just have that as a backup. And then like you have like a whole bunch of files that are like commented stuff out and like such and such old or whatever. And right before I quit working on the project, I made sure to get everything kind of cleaned up and put it on a GitHub repo so I can come back to it later. And I kind of had to relearn how to use Git and everything recently, but I use a extension called GitLens, and it makes handling a lot of the Git stuff a lot easier because we can see just like the different branches, the different commits and everything. They have like a premium feature thing, but it's not really necessary for the stuff that I do. It's better for if you have like a big team, but just for myself, this is awesome just because I can quickly and easily just stage things and commit things and all that kind of stuff. So let's see. Oh wait, let me go to the next song. Okay. Let's see. What's sick about using like Vite and like Node, or not Node, but there's a couple of other frameworks where they have like the live reloading kind of stuff. So you update something, hit save, and then it automatically just reloads over here. It's really, really sick. I love working that kind of way. Sweet. Okay, with that, I will be right back. Okay, I'm back. Had to get some food. But now I am replenished. Let's see. Where was I? Okay, we were following along with this tutorial, kind of watching it, but also kind of not watching it. Mostly just getting the starter. Let's see. Okay, and so like the first thing that we're gonna try to do is from this bare bones starting point, we're gonna try to get this set up. We're gonna try to replicate this, and we have a few things working in our favor, or things to pull from. Number one is just the code for this demo itself. But this is a really minimal example that uses basically a more simplified physics system and like the collision detection. It's a very outdated physics engine, or it's an outdated collision detection system. It uses an octree, and I only know a little bit about octree. I mean, I know like functionally how they work, but I can't really explain them off the top of my head. I'm not that deep into computer science stuff, like just the core fundamental stuff. But so we're gonna try to recreate this. It's gonna be mostly like I don't know, like we're not gonna pull it one for one. It's gonna be like a functional starting point. We're gonna be pulling from let's see, and I'll put up this Google Doc later. Some random quotes and stuff. This right here. Here's a demo, a very functional demo of Three.js working with Rapier JS. And what I like about this project, and what they one thing they were talking about, is this is an example of a non-trivial Three.js project with a bundler. Like a lot of the other examples, like this one, for example, if we go, let's see, we click this, and click, okay. This is the full file for that first-person shooter thing that we just saw. So it's only 500 lines of code, and a lot of it is just like it's has everything, including like the stuff, like the base level Three.js stuff of like setting up your different key bindings, and then your animation loop. Like everything's in here. It's a very simple implementation. So let's start from the beginning. Okay, so here's just your imports and stuff, getting your GUI, your clock. So first, they're setting up the lights in the scene, setting up the renderer, setting up the little stats element up at the top left, defining their gravity, defining the number of spheres and the sphere radius, steps per frame, that's what I was talking about earlier about how it's important to have your physics simulation running at a faster speed than your rendering. Let's see. Sphere geometry. This is basically like how all objects in 3JS are defined. You have some geometry. It's just your like, just basically lines put together that make a shape. No painting, no texture on it or anything like that. And then you can think of it kind of like a wireframe setup. Like if you're making something out of pipe cleaners or like toothpicks, like making a toothpick sculpture, it's just the line work, just the geometry. And then basically you go over it and wrap material around it. And there's like the predefined basic materials that come with 3JS. Let's see. And then so what this is doing is setting up an object, an array to hold the spheres, and then it's going to basically make a pool of spheres to shoot from. So like it's going to go through maximum of 100 spheres right here, and then it's going to shoot the first sphere, and then once it hits 99, the 99th sphere, it's going to loop back around and make that first one disappear, and it basically starts the pool, starts the cycle over again. And so what it's doing every time that you shoot, in this case, in this example, it's okay, so we already have the sphere geometry and material defined right here, and so whenever we are making these spheres, it just pulls from those definitions that are already up there and says, hey, this is what a sphere is going to be shaped like, this is what it's going to look like, it's going to cast a shadow, it's going to receive a shadow, and then we put it in the scene. And then let's see, what is this doing? So this is the spheres.push, that is adding that into the array. So it's going to go through and go, as soon as the game starts, it's going to go ahead and initialize this and set up 100 spheres in this array. And let's see. So the collider is a sphere around the already existing sphere. So this is the one thing that it took me a while to wrap my head around when I was just like digging my feet through this, dragging my feet through this, trying to figure it out initially, like 2 years ago, is that I didn't understand, like I had learned how to do like 3JS stuff regularly, but incorporating the physics element of it, I didn't really get it off rip, because let's see. Not dark mode this. So I had made this website using 3JS, but there's no physics in this. It's all just displaying things, displaying models or geometries or whatever. So I knew how to do this, but as far as incorporating the physics elements into it, I didn't understand. And basically, there's two different worlds. You have your visible world and you have your physics world. And that's basically how most engines that I'm aware of work, is that you have your graphics side and then your physics side. So for each sphere that we have that has geometry and everything, we also have an invisible copy, an identical copy, ideally. It's not always exactly identical. Like, for example, if you're like your player collision, your hitbox, sometimes that doesn't align 100%. But ideally, like for this, it's a sphere, so it's really easy to make it identical. But each object has an invisible geometry associated with it that's used for calculating the physics. And so that's something that took me a while to just realize and understand, because I was working on trying to make the game, and I would have like the visible objects in there or something, or I'd have like the physics objects, but then I wouldn't see the visible representation of it in the scene, and that's where I was kind of confused. But so basically, this is setting up the sphere as having the mesh, which is going to be this right here, which is the sphere geometry and sphere material. And we've already said that it casts and receives a shadow, and it's in our scene. That's defined as the mesh. And for this particular ball, the collider is going to be a sphere that's the same radius. And let's see, what would this be? This would probably be the that'd be, what would this vector be? It's not the gravity, I don't think. Trying to think if in 3JS if y is up or it's depth. It's different depending on different 3D engines. I'm not sure exactly what this vector is defining. I guess just position. Oh, well. Why is it negative? Maybe that's gravity. I guess that's gravity. That's my best guess. So I guess somewhere in here we're going to take that value from the vector and multiply it by gravity or something like that. We'll find out later on. And then a velocity, and it's just an empty velocity, but it's going ahead and defining it. So each object that's in this array is going to have these characteristics. And then this is what I was talking about, using like a more outdated or more rudimentary collision detection. It uses the octree, and then player collider, little capsule. Give the player velocity, direction. Just, they're empty right now, empty objects, but we're going to go ahead and define them. Simple little check to let it know whether the player's on the floor or not, so that way you can, what this is used for is to let the game know whether or not you can jump. So that way you can't just double jump and continuously jump when you're in the air. You have to be on the floor to be able to jump. Key states, I'm not sure what the key states. I guess key states are, let's see. So we got our key states, our vector. So it's going to listen for... Oh, okay. So this is basically setting up, looking for, like, the definition for whenever it's going to look for a key press, a release, and when we click, and when we release the click. And then so it's going to take these event listeners in the event code, and let's see, somewhere around here. Okay, yeah, so that vector right there, well, I'm still not sure. Wait, let me see. I'm still not sure when the collider has this vector. I guess just to determine which side is the right side up. I'm not sure why it would matter on a sphere, though. Yeah, I'm not really sure. I'd have to poke around and look at the what that's doing. Let's see. So basically this is listening for all of the keys that are pressed and all the keys that are released. And I'm assuming whenever it detects a specific key, like the W key or whatever, then it gets that and uses that for like movement or whatever. So it's constantly listening for the keys that are pressed and the mouse that's being clicked. Your standard window resize. So throw ball. Okay. So this grabs whatever is the current index of the sphere in our array. We're going to get whichever direction that we're looking at, whichever direction the player is pointing. And then we're going to take the physics element of that current sphere that we're throwing. We're going to get the slider center. We're going to copy it. So we're going to get that position of the sphere center where it starts. We're going to put it at the outside edge of the player, and then we're going to add a force that is facing in the direction that you're looking, and it's going to start at the edge of the player's radius, and it's going to be with a force of 1.5 whatever units. So that's how it's going to, let's see, wait. Add scale vector. Oh wait, no, hold on, wait. My bad. This is going to set up, it's going to get center of the sphere, put it at the outside edge of the player's hit detection, and put it a little bit further out. Because if it was a little bit closer, because this is a very simple example, let me show you. I can just demo it. Since this demo is very simple, it goes ahead and puts the ball a little bit further away from the player capsule. And where this falls apart is because if you shoot down, even though it's within that certain distance away from the player's hitbox is a capsule, so it's tall. It's taller than it is in its radius. So shooting, horizontally like this is fine, but then when you look down, it catches that bottom of the capsule. So that's what that part of the code is doing. And then this is the one that actually applies that force. And they have some sort of math set up here. What is this? Interesting. Not sure how this math works, but we'll figure it out later. So it's going to take the current velocity that the player is moving at. So if you jump or run through the air or whatever, and then you throw a ball, the ball's speed versus velocity doesn't start out from 0. It starts out from whatever the player's currently at. So that way, like if you are running really fast and shoot a ball, you don't outrun the ball and run into it. So then we add the scaled vector. So there's there's the impulse. Okay. So yeah, it goes ahead and gets the velocity that's in the player's direction, and then multiplies it by the impulse. Okay. And then this is the one that actually defines, it makes it faster than wherever the player is moving at. I see. That's play direction, that's velocity. But yeah, like I was saying, it's so you don't outrun the ball that you just shot. And then this says, hey, I used that ball, it's done. Let's move to the next ball. And then this is the really simple collision detection that I was talking about. So it's using, let me look up what an octree looks like. It's like a branched tree like this. So that's what that like BVH thing that we were looking at a second ago. Hold on. 3 mesh deviation. I can show it a lot better with this. Okay, display BVH. Okay, so we can change the depth. Okay, so this is basically using an octree kind of thing. Just a more advanced version of that system. So what it's doing in 3JS is basically making little simplified representations of things that are going on in the scene, the geometry in the scene. And this one is a more robust system of doing that, that allows for more customization of functionality and everything. So this is the depth of 1, and you can see like the boxes are pretty big. I mean, these are obviously like as small as they need to be, but as we start to increase the depth to, let me go back to 1 and now to 2, you can see there's a few more little smaller boxes, and so on and so forth as we increase the number of the depth that we're at. So what that's doing is going down the line, and it's starting out from like the very simplified big boundary box, and then it's breaking it down into smaller and smaller pieces as we go along. That's basically what's going on with this player collision. So it's saying, hey, look at the world octree, look at the current look at the player collider compared with the world that we've set up, and see if the player is colliding or intersecting that other boundary box, basically. So this is where we set the player on floor thing. So saying if we collide with the floor, then we are touching the floor, and therefore we can't jump. So this seems to like make it where we don't fall 100% as fast as we would in real life. There's a little bit of dampening to the gravity. Saying add the player velocity, add the vector. Currently we're moving towards with the dampening. Okay. Huh. Still trying to figure this out. Oh, okay. So basically, this part right here takes the player's velocity and then applies the dampening. The delta position takes that player velocity, clones it, multiplies it by the amount of time it takes to render one frame, and then after that is calculated, that's our new position. So we're going to move the player's collider to that new position. So first it calculates it, then it actually applies the movement, but it's pretty much right after it. So it happens really quickly. And then we update the player collision and check and see if the player is on the floor and if they can jump or not. And then we also move the camera position. So first we calculate where they're going to move to, then we apply it, we check to see if they're colliding, and then finally we update their camera position. And then this is this is checking to see if the sphere is hit the player. I'm gonna skip through some of this. I'll come back to it tomorrow. Getting kind of tired. I'll probably keep working for like another, I don't know, 45 minutes, an hour or so. I just mostly wanted to get the project set up and get the groundwork laid out today. I'm going to be referring back to the stuff that I'm showing you a lot, but I just wanted to kind of refresh myself on how this stuff works. Because I kind of I was looking at it and reverse engineering it to use with the ammo physics engine 2 years ago. But it's obviously been a while since I've looked over this. Yeah, so this is looking for if it's W key, S, A, D. If the player's on floor, then it allows that space to add a jump. This is actually, this is going to go ahead and load. It's going to set the path for where the 3D models are going to be pulled from. This is the actual level. Going to add it to the scene. It's going to generate that octree tree that we were looking at a second ago, where it breaks it into those smaller boxes. And then it's going to go through all of the objects in the scene that are a child of. Let's see. So it's going to load this 3D model as GLTF. Then, if that object has any children that are a mesh, then it sets them to receive a shadow and cast a shadow. And if that is the material that it's looking at, then it's going to set this material to, I forget what, and how do you pronounce this? I've never actually verbalized it. Anistropy?
Elastic asymmetry and material anisotropy. So the cellulose orientation again is in the cortex.
That stands for the Wilkinson Microwave Anisotropy Probe.
And so on.
Anisotropy. Anisotropy. Okay. What is anisotropy? What is anisotropy? Anisotropy. Anisotropy. Give me a picture. Oh, I see. This is a nice demonstration. That makes it really, really clear to me what it is. Okay. We'll come back to this another day. Let's see. wonder if we can, oh wait, debug. Oh yeah, okay. A little complicated stuff. Oh yeah, so this is the octree that I was talking about earlier. Where it's breaking this 3D model level down into smaller chunks for the purpose of calculating collisions. There's for the flat parts like this, not a whole lot of crazy geometry going on. But then when we get over here, a lot more boxes, a lot more geometry that needs to be broken down. And I have my bitrate pretty high right now, so I think it shouldn't be too blurry on screen, especially since I'm only streaming at like 30 FPS right now, so it should still come through the video okay, even though there's a whole bunch of like lines and stuff. It still looks somewhat decent. Just an out of bounds thing where it teleports the player back to the start. Yeah, they look for collision and substeps to mitigate the risk of an object traversing another too quickly for detection. And that's why the steps per frame is 5. Because it's going to run through that physics calculation 5 times for every visible frame that shows up. But what's interesting, and I think this is just because of how they have the like it's set to be like, hold on. This part right here, where it takes the sphere's center, and then it gets the outside of the player capsule, and then it adds a vector in the direction that the player's looking, and the player at the end of the player's collider radius multiplied by 1.5. So it's putting it lightly outside of the hitbox of the player by 1.5 times. And then because of that, so like you can shoot just fine. Let me turn off the debug. I guess I can leave it open just for demonstration purposes. But then when we can shoot, and that's why we're able to have that kickback, is because they have the functionality in there to detect if the balls hit a player. But so we can shoot and everything, and it's fine and dandy or whatever, it bounces at the wall. But if we get too close, I'm shooting right now. So let me get right at the edge. Click, click, click. It goes right through the wall, and that is because we're spawning at 1.5 times outside of the player radius. That's just an interesting bug that I found in this. Let me turn off the debug now. So let's see. Oh yeah, I was gonna show another bug. So there's the bug where it hits the bottom of the collider, but I found out like you can get a pretty cool like rocket jump kind of ability from that. So I might want to keep something like this in the official version of the game, like not this much of an impulse or force added to the player's movement, but I don't know, just something about that mechanic where you look down and then shoot across the map. It's just really cool. I want to see how it'd play out if you had 2 people like shooting around the map and then, I don't know, just flying around and stuff. Let's see. Yeah, see, here's the part we go out of bounds and it puts us back in there, but you'll notice that we still have our momentum whenever we spawn back in. Pretty cool. Let's see, what was another glitch? I think it's most of the main glitches that I've found. I'm still not 100% sure. I mean, I get that this is happening because it's getting the shadow mapping from that. I'm still not 100% sure why it's showing up here though. But we'll figure that out later. Let's see. I'm so sleepy. Oh yeah, and in addition to this demo, this basic tutorial, we also have this example where they use instancing. So basically, the reason this is able to be so performant, aside from the fact that it's using the Rapier physics engine, is the fact that all of these identical objects, like the spheres and then the cubes themselves, they're all basically the exact same. Like, they're just a copy. Like, these are just direct clones of each other. So there's one like piece of geometry that all the others are pulling from, and so because of that, this physics and the scene, the rendering of it, is basically able to treat it like it's just the same object, just copied a bunch of times. So it's very, very performant because it's just having to perform the calculations essentially one time for like the geometry and the material calculation, like rendering the material itself, like actually forming the light bouncing off of it. And this is, I'm gonna try to disable my dark mode thing for this scene, but yeah, that's why this is able to be so performant. It's because to the physics, or to the 3D renderer, all of this objects with the same shape are essentially just, it has to perform that calculation once. Hold on. So each mesh has a geometry and a material. Usually, the mesh has a specific geometry representing like a single character, a chest, a car, whatever. And rendering that mesh requires moving its individual vertices. So that would be like a corner. Like if you imagine like a cube, like this is a vertice, this is a vertice, this is a vertice. So it basically involves moving that vertice and the material. So you'll notice there's a different color on each side of this. That's because this material is set up to have different colors on each side or whatever, and have different reflective properties or whatever. And it's sending that information to the graphics card to be rendered. And each mesh has to be done separately. But if we have the exact same character, exact same model, instead of creating 10 separate versions of it with 10 separate draw calls, you create one single mesh and duplicate the geometry 10 times. And then for each of those duplicates, they all have the exact same geometry, exact same shape or whatever. You just kind of move the simulated location of it, making it look like it's 10 different objects. So the way this is going to affect what we're making is that all of these spheres are going to be essentially one sphere just cloned and in slightly different positions and velocities and stuff. But that is going to be roughly what we're going to do to make it the actual graphical side of things be very performant. And it's why an example, a demo like this is able to be ran on a cell phone. It's because like there's still a lot of physics stuff going on, but the thing that would really kill this on a phone is the fact that it if it wasn't doing instance geometry, if it wasn't all the exact same cube copied a whole bunch of times, then that would be a lot more graphics calculations to perform. So yeah, that's that. Okay, I think I'm gonna go ahead and end stream for right now. I'm gonna hop back on tomorrow, and what we're gonna pick up with this is we're going to be basically trying to recreate a very, very basic parts of this demo. We're gonna try to get a floor. We're gonna try to get a player capsule or player character that we can move around, and we're going to have the ability to click and shoot projectiles. That is what we're going to shoot for tomorrow. Should be fairly straightforward, especially since we have the example code to pull from right here, and then we also have hold on. And then here's the code for instancing, and this is actually specifically for the Rapier physics engine, which is what we're going to be using. Now our actual use of it is going to be different because some of this stuff is abstracted by us using it in React 3 Fiber or React 3 Rapier. So that's why like orbit controls is just that right there. If we go into the like here, let me find the corresponding code. Okay, so here, right here, this is the raw 3JS code where we're making a camera, setting the FOV to 50, and then setting the window width divided by its height to get our aspect ratio. That's probably the minimum view distance, and that's the max view distance. And then we got to set the camera's position, which directions it's facing at. And then over here, it's basically just abstracted and simplified down to just giving it a position, FOV, and saying, hey, I want shadows. So a lot of the stuff that we're going to be doing, a lot of the reason that I'm using this framework is because a lot of some of the stuff like that, it's more basic stuff. Like, it's like I know how all this stuff works. It's just kind of annoying to have to redo this or make your own components or whatever. There's like a lot of built-in functionality, and this particular library, it comes with some of the physics aspects of it already incorporated into it. Like, there's nothing right here with physics, but it's in a similar fashion, kind of abstracted away, so it's a lot easier for us to interact with. Like, we can get back down to the nitty-gritty and add some of the functionality. Like, if we wanted to adjust like the max and minimum view distance, like, we can do that, but we don't have to. It's already defined on the back end. So yeah, most of this should be pretty straightforward tomorrow as far as just getting like the base level stuff, like adding a floor, adding a player with a controllable hitbox or whatever, and then being able to spawn spheres and shoot them in a direction. The core components should be pretty straightforward. Because like I said, we have the instancing example right here where it's going to get, let's follow through this. So we've got our lighting, we've got our camera, our floor, got our floor position, say receive shadow, we add it to the scene, we add it to our physics world as well, which is important. Material, I don't know what this matrix is for. Color, where is that used? Okay. I see. So it's basically splitting up the world. I don't know, I have to come back to this. I'm not exactly sure how the matrix is being used. I know this is like a random X, Y, and Z. Setting position. I don't know, we'll have to come back and figure that out. But that's for tomorrow. Yeah, so we're setting our box geometry. So it's just a regular cube. we're making our new 3 instance mesh. Interesting. Yeah, I've never used instant meshes. But I know they're the way to go for what we're doing, because it's a lot of the same exact geometry. But you know, it'd be sick though. One thing I want to add is squash and stretch. So like whenever a specific sphere hits a wall, it gets kind of squished up against it when it bounces off. I think that'd be like late stage after I get most of the basic stuff set up. I think that'd be a pretty cool thing to add. Like if it's going really, really fast and hits against the wall, it like compresses like a tennis ball or golf ball. But yeah, this is getting the basic geometry of that, setting it as an instance mesh so you can make copies of it, and then spawn them at a random height or a random XYZ coordinate within a limit. Or, well, not within a limit, but it yeah, at the core, it's basically setting the geometry, making the copies of it, adding the physics, or adding each of the boxes that are in the array to the physics world. Doing the same thing for the spheres, adding them to this physics world, rendering it, setting up our movement controls, animating. What is this doing? I guess, oh, this is just setting how fast everything happens. Not sure. There's some things that I'm confused on, but we'll figure it out tomorrow. The beauty of doing things now, as opposed to 2 years ago, is now I can just drop some of this code into ChatGPT, have a really quick answer of what it's doing. It's fire. Yep, that's it for tonight. Yep, I'm looking forward. It's gonna be fun. Not sure how long this project is going to take me, but it's something I've been wanting to do for 2 years. I mean, it's not like my desire to make this is going to go away. And the only reason I kind of abandoned it last time was just because I was grinding away at it for like a month straight without doing anything else, while also still having to like go to a physical job or whatever. My new job now, I work from home, so I have like a lot more time and also a lot more flexibility. Like if I want to just like work on the stuff that I'm working on for my job and then like take a break 2 or 3 hours, work on this, and come back to the regular work, I can just do that. So a lot more flexibility with my time and everything, mostly just because I'm still here at the same desk or whatever. But yeah, I'm excited. It's gonna be fun. Yeah, we're gonna get this set up single player first, and then we're gonna try to start incorporating in some of the the server elements of it, and then get into the more complicated like state replication kind of stuff. sending like snapshots. Just gonna take it one step at a time. The tools are out there, possibilities out there. We just gotta make it happen. Like I'm 100 billion% positive. I'm sure that it is completely possible and entirely within the realm of possibility to make this physics-based first-person shooter multiplayer game in JavaScript in the browser. I know it's accomplishable without a whole crazy amount of lag. I know we can do it. We can do it. But yeah, thanks for watching. I'll see you later.